All right, I want to take some time to go over some of the key things that we discussed last class about condensation reactions. And this is going to be a mix of prepare questions, box problems, provide the products, or even mechanistic. So this is a question where I have an aldehyde and it says that I have NaOET, that's my base, and ethanol, and it's in cold, and I'm supposed to provide the products for that. So realize this is basically aldol condensation, since that's my base here. It's essentially step 1, alpha hydrogens that we are seeking, which we are going to remove. And so you're going to see one of these molecules that will behave like an acceptor, the other that will behave like a donor. So this is my acceptor. I'm going to make the enolate of the other one. So OET is going to come in, pick up the proton, electrons move, and now we are going to just show the opposite of what we have. That means the donor is going to attack the acceptor, electrons move, and you have, so let's just number it, 1, 2, 3, 4, 5, and I have 1, 2, let's call it 6, 7, 8, 9, 10. I told you in class that the rule is that the donor gets to keep all of its carbons. So that's carbon 6, 7, 8, 9, and 10. And 7 is connected to 1. So this is my new bond. Let's just show that in a different color. This is my new bond. And I'm going back to the red or burgundy. O negative. That's 1, 2, 3, 4, and 5. And now, of course, it's going to exchange the proton with ethanol, which is your solvent. Always pay attention to, because some of those questions in the take-home quiz, some of you were not paying attention to the solvent. You can't just randomly pick any solvent. You have to pay attention to what you have here. If it's ethanol, use that. If it's methanol, use that. If it's water, then use water. But you have to pay attention to what's given. Don't just create matter. It's a beta hydroxyaldehyde. 1, 2, 3, 4, 5. So that's going to go through the reaction, and that's your aldol. Now they just stopped at ethanol cold. They haven't done the acid step. If they put an H plus an acid, then you can show the release of the water as well, and so your product in that case would be it would look something like that. Okay, so 1, 2, 3, 4, 5. We're good. But obviously, if it doesn't say so, if that step, the H plus and the heat, if that step is missing, don't worry about it. Don't show it. All right, let's take a look at another question. The question I have here is that I have a cyclohexane. This is similar to actually something that we did last class, yesterday. So we have a cyclohexanone. It's a dimethyl cyclohexanone, and I'm treating that with an ester. So hopefully that little sequence, the little cheat sheet that I created for you, you can envision that you should get a dicarbonyl compound at the end of the day. Sodium ethoxide, ethanol, that's your first step, and they do want to treat it with acid. Okay. All right, so hopefully you can see here that in this particular case, we have sort of fixed our acceptor. we have fixed our acceptor, okay, and we have fixed our donor as well. What I mean by that is you had two choices. You had one and another alpha system which could have reacted, but since one side contains only the dimethyl, there are no protons, so that side is not going to participate in enolization. It's only the right hand side which is going to participate in enolization. And of course I say that the second molecule is the one that's your acceptor, because you don't even have the neighboring alpha to lose. So your first step will be that you will show the loss of proton, looking for the most acidic protons. So those are going to be right over here. The ethoxide comes in, picks up the proton, electrons move, you end up with an enolate. This is going to be your kinetic product, of course, and only product, so kinetic and thermodynamic rather. Electrons come back, attack takes place, electrons move on oxygen, and first you get the beta keto ester. Let's show the negative charge. When the electrons kick back in, the OET leaves, and you end up with one carbonyl group within the ring and another carbonyl right outside. So it's a dicarbonyl system that you're going to get at the end of the day. This ethyl formate, I talked about this last class also, but ethyl formate is a great way of putting ethyl formate or methyl formate. Those are great ways of putting in a CHO group. This is a CHO group, an aldehyde group, via a Claisen type condensation reaction. Okay, it's time for a box problem. So let's see what's going on here. We have two ester groups. So we have an ester here and an ester here. We are going to treat it with basic conditions. Notice I'm still keeping my OET consistent with the solvent and the base, and then I'm supposed to treat it with acid, and then I'm supposed to again treat it with some kind of a base, and ultimately with some kind of a alkyl halide in this case, and we'll see where we go from there. So whenever you have a two ester type system, you're basically talking about Claisen condensation. And so of course your product will be a keto ester. From my little, again, cheat sheet, keto ester is what you expect. And if it's a keto ester, and I said in class that if you have, like a system in which you have the donor and the acceptor within the starting material, then the snake is supposed to bite its tail. That means we are talking about some kind of a cyclization. That's one thing. And the other thing I would like to say is you have 1, 2, 3, 4, 5, 6, and 7. So it's a 7 carbon ester. That means the size of the ring is supposed to be, you got it, 6-membered chain or 6-membered ring. So let's take a look how we are going to go about this, and how would you decide which side should be the donor and which side should be the acceptor. Now, if you ask me, I would say that the most acidic proton is right here at 6. And the reason for that is because carbon number 2 is very close to, 3, which has these two methyl groups. And so they are going to A, provide the steric bulk, and B, they are going to also provide the inductive effect. And so I would say 6 is going to be most acidic. And so that's the carbon from which you should remove your protons. So your structure will look like this is 5, 6, 7, this is 4, 3 has the two methyls, 2, and then OET. And now it's time to push some arrows in getting the ring. And so negative OET, and that's 1, 2, 3, 4, 5. It's a bond between 6 and where did it go? 1. And then the electrons kick in and they kick out the ethoxy group. And what you have is going to be your first product. So we are up to here. The question then says that you're supposed to treat it with sodium ethoxide and then treat it with the alkyl halide. So now when you treat it with sodium ethoxide, you're going to get rid of the most acidic hydrogen, which is right here, the one in the middle, and you're going to end up with the anion. Of course, the two methyls are still there. So that anion is then going to react with your alkyl halide, and you would have a substituted ring system, new substitution there. So let's just draw that as well. And 3. That's going to be our product. Now if they further treat it with an acid and heat it, then this entire ester would also go away. So let's say there was a fifth step to that they treated it with hydronium and they heated it, then that means, this just means proton exchange that took place. So ethoxide would become ethanol. But this tells you that the entire ester group will go away, and in that case your product will look like this product. Alright, let's take a look at a fourth problem. So this is what is given. Hopefully again you can realize that we have to look for the most acidic hydrogen. That's step 1. And so hopefully everybody here can see that the ones in the middle are the most acidic hydrogens. So the ethoxide is going to pick those up. Electrons move again. So you have your enolate double bonded COOET plus your alpha beta unsaturated compound. And so hopefully you also remember that the alpha beta unsaturated compound has your incoming nucleophile going in at position 4 rather than position 2. So as electrons kick back in, the attack is going to take place at position 4. So you will see oxygen with negative charge, double bond. This is a new bond that got formed. It's going to a COOET. It's also going to another carbon. So I'm just going to number these so you can follow along. So 1, 2, 3, and 4. That means I have 1, 2, 3, and 4. And let's call this 5, 6, 7. This is 5, 6, and 7. So the new bond is right over here. of course the electrons will come back in. The charge is going to get satisfied by just picking up a proton from the solvent, COOET, and you have a, and now depending on the reaction, what the reaction is, this of course was a box problem, so this is what you draw. But if the question takes it further, and the question expects you to treat this with a base, and now you have to remove a proton, or you have to circle, let's say, in the product, provide the most acidic proton. So what would you say? You would say this is the one which is in between two groups, so this is the one that will be removed if we have to do that. And you can put in an alkyl group the same way that we have been doing. If somebody asks you, what is the name of this reaction? You would say this is Michael reaction. And the reason why it's Michael is because you're using the alpha beta unsaturated ketone as your acceptor. Okay, let's take a look at a box problem. You are supposed to give me the structures of the two compounds which upon treatment with sodium methoxide and methanol will give you this product. And the easiest to go about this is to basically go backtrack and cleave right over at the double bond, which is a part of the alpha beta unsaturated system. And as you do that, hopefully you can see that part of this is going to come from, if this were a ketone, and this were an ester. And so hopefully you can see that essentially this part of the molecule was your donor, and this part of the molecule was the acceptor. So these boxes might just say something like, what is the acceptor and what is the donor? So you put the respective structures in those boxes. So in my head, when I think about it, what I like to do is, since the second step, which is, once the aldol product gets generated and then we treat it with acid and heat, and basically water molecule is given off. So in my head, what I try to do is I try to put the water molecule back into the system. And so I say the double bond O goes in one direction, so you would be adding H2 to the other side. Another way to see that, more just a quicker way to get there. But so what you need to understand here is that the most acidic protons will lie between the two carbonyl groups, and so that has to be your donor in this case. Okay, let's do a prepare question. You have to go from one to another. I have said this umpteen number of times. The number of arrows has got nothing to do with the number of steps. You can choose as many as you want to. That just tells you more than one arrow just means it's multiple steps. That's it. All right. You have a ketoester, and you end up with a dicarbonyl compound. Notice, in doing so, we are getting rid of the ester. That means, and since it's a keto ester, that basically means that I would be using the hydrolysis treatment with the acid and heat part at some point of time. And that basically tells you that at this location, you are supposed to put in, a chain like that. Now, how can you put in a chain like that? Well, there are multiple ways of doing that. You can have something like a Michael acceptor. And since you know that the polarity of that exists such that the carbon number 4 is the one which is most electrophilic, essentially when you treat your ketoester with a base and treat it, with your Michael acceptor, you're going to see OMe, negative charge, attack takes place, electrons move, and you have OMe and the 4-carbon chain, 1, 2, or 4-atom chain rather. That's what you would get. And now we are going to just treat it with acid and heat it, and that will get rid of the alcohol as well as the CO2. So that's decarboxylates, and what remains is your product. Okay, let's talk about a box problem for this particular video. I think that's the 5th or the 6th problem. So I'm treating this alpha beta unsaturated compound, and that's all I have for now. And I'm treating that with LDA. So LDA is a base. It's going to take away the most acidic proton. Realize the only acidic protons that are present are right over here. You don't have anything on the other side because there's a double bond, and you cannot quite remove protons from that particular position. And so you would see a negative charge over here, and you can show that as, you know, this coming in, it has resonance, so you can show that as the enolate. And I'm then treating that with the Br here and the Br here. So electrons move in, electrons will attack at the carbon, Br leaves. So you get double bond, carbon, carbon. Let's number it 1, 2, 3, and 4. Is that 4? 1, 2, 3, and 4. Yeah. So 1, 2, 3, 4, and Br. And then I'm treating it again with LDA. Well, guess what? We have one more acidic hydrogen right over here, which can be removed. So again, the enolization will take place. And when the electrons come back, you will ring close, and bromine is going to leave. So you will show the attack, bromine will leave, and you will end up with a 5-membered ring. FYI, for anyone who's interested, these compounds, which are sp3 hybridized and they have 2 rings on each side, are also referred to as spiro compounds. Okay, a reminder, Grignard reagent with alpha beta unsaturated ketone always does 1,2, it never does 1,4. So you're going to get an OH over here and a pH over here. That's your product.